We have 2 more lectures to go, today and Monday. And I thought might be interesting to switch gears a bit, and now that we've basically completed the cosmology part, and that we now head towards the Hawking effect. So today we'll do the Unruh effect again, but from a very different perspective. This time not with an Unruh-Debye detector that's being accelerated, but this time with Bogoliubov transformations. And that will prepare us then for a particular approach towards deriving the Hawking effect, Hawking radiation, on Monday. So today, the Unruh effect again. We'll do that in 1 + 1 dimensions because it's technically simpler and we don't really miss out on any generality when doing so. We will use the metric convention where the metric in 1 + 1 dimensions is 1, 0, 0, -1. So now let's consider the trajectory of an observer. So we write it as x alpha of tau, and we use as the parametrization of that world line of the observer the proper time of the observer, the proper time tau. We could use another parametrization, but that's the parametrization we choose. Because later we want to change to a coordinate system which is adapted to the traveler, for whom then this proper time will be the time. So then the velocity, the covariant velocity vector of our, or the relative, I shouldn't say covariant because it's actually contravariant. The velocity vector of our traveler is then given by dx by d tau, and we indicate the derivative with respect to the proper time by a dot. There's a little proposition which says that the invariant length of the velocity vector is 1. No matter what trajectory the observer undergoes, the length of the velocity vector is always 1 if we choose for the parametrization the proper time. Let's quickly prove that. At some time t, let's choose a rest frame, a frame which is moving along with the traveler, and in that rest frame, the coordinates of our observer are going to be tau, the proper time, and the position is 0 because the coordinate system is moving along with the traveler. So therefore, the velocity vector is simply 1, 0, because we're differentiating the position with respect to the proper time. So that gives us a 1. When that's differentiated, that gives us a 0. And the length of this vector here is given obviously by 1 × 1 minus 0 squared, so it's just 1. But that quantity is a scalar. It doesn't matter in which coordinate system you calculate it. And so indeed the length of the velocity vector, and in general you can make the same argument in higher dimensions of the 4 velocity vector, for example, is always 1. If you parameterize your trajectory by proper time. Now let's look at the acceleration vector. Acceleration vector is obtained by differentiating the velocity vector with respect to the proper time one more time. There's again a little proposition which says that these 2 vectors are covariantly orthogonal to another. The acceleration vector is always orthogonal to the velocity vector. And here's the quick proof for this. Let's just take the velocity squared and differentiate it with respect to tau. We get 2x double dot x. But the length of the velocity vector is constant. It's always 1. So the derivative is 0. So we have that 0 is equal to this, which is what we had to prove, that these 2 are covariantly orthogonal to each other. We can use that. Let us look at the rest frame again. In the rest frame, the velocity vector looks like this. Remember, we work in 1 + 1 dimensions. And so what is the second derivative vector, the acceleration vector? Well, the acceleration vector must have a 0 here in the rest frame, because in the rest frame this is always the velocity vector. So we have a 0 here, but there we may have an acceleration. Now what's the length of this vector, of this acceleration vector? Well, the length is going to be this squared minus that squared. So the length of the acceleration vector is given by minus a squared of tau. The a is d squared x1 by d tau squared. So that's really the acceleration, literally the acceleration in the rest frame. So in every coordinate system, in every frame, we have that the length of the invariant length of the acceleration vector is given by minus a squared of tau. Now let's specialize to a trajectory that is the trajectory of a traveler who travels with a constant acceleration. So we now assume that this a of tau is actually constant for all tau. Then here's a proposition, namely that a trajectory, other trajectories exist, but a trajectory of uniform acceleration is given by this. You know, we can also translate and so on, and we can shift the trajectories in time and in space. But here we have a trajectory of uniform acceleration, or of constant acceleration, and it is given in this way. The trajectory, the world line, parameterized by proper time, and having the coefficient functions t of tau and x of tau, is given by 1 over a being the acceleration, hyperbolic sine of at, and 1 over a hyperbolic cosine of not of at, of a tau. Let's prove that this really is a trajectory of uniform acceleration a. We calculate the derivative of it, the velocity vector. So we differentiate this and that with respect to tau. The sinh becomes a cosh, and we just get rid of this a here because of the chain rule. So we have here the hyperbolic cosine, hyperbolic sine. And if you remember, the cosine squared minus the hyperbolic cosine squared minus the hyperbolic sine squared is 1. So indeed, the length, the invariant length of that velocity vector is 1, which tells us that tau is not just any parameter, it's the proper time. Now let's check what the acceleration is. So we differentiate this again with respect to tau, and then this becomes hyperbolic sine, hyperbolic cosine, but we get another factor of a. So this is now the acceleration vector here. And let's check what its length is. Well, the length is given by a squared times sin squared minus the cos squared, which is 1, but multiplied with a squared. So the invariant length of the acceleration vector is given by minus a squared, which is what we wanted. This trajectory that we just investigated also obeys this hyperbolic equation. Let me show you why. Here's the trajectory again. And if you square the t coordinate and you square the x coordinate, you can use the trigonometric identity between the hyperbolic sine and the hyperbolic cosine, namely that hyperbolic cosine squared minus hyperbolic sine squared is 1. And you obtain that for this trajectory, we have that the time variable squared minus the position variable squared equal to minus 1 over a squared. So here's the diagram, space to the right and time upwards. So this is a inertial coordinate system, an inertial Cartesian coordinate system. And light would travel here in 45 degrees. And our observer is on this hyperbola. Our traveler comes from here and moves onto there. You know, this is the time evolution here. Intuitively, our observer comes in from plus infinity, from far away, comes in like this, and then decelerates, right? It gets slower and slower, and when it hits the axis, its velocity is actually 0. It's no longer moving in this or in that direction, so its velocity is 0, and then it starts accelerating this way. So overall, it's a constant acceleration. It's just that it started out with a velocity that it has to bring down to 0 and then reverse. So what you see here is that our traveler comes asymptotically close to this 45-degree line in the past, and it will also asymptote towards that 45-degree line in the future. That will be important later on. Because what we see here is that our traveler actually has two horizons, a future and a past horizon. And these horizons are given by this line and by that line. By the line t is equal to plus x, and by the line t is equal to minus x. See, when you look at our traveler here, this traveler will never get news about events that happened above that line, above that 45-degree line. Because every event that happened above that line can only transmit information in its forward light cone, which can be only as steep as or as shallow as 45 degrees. So any event that happens, for example, here, can only message this way, that way, that way, but it cannot message at a shallow enough angle to actually hit the traveler. So the traveler is going to be ignorant. It cannot be influenced by any events over there. So this represents a horizon for our traveler. On the other hand, events that happened below that 45-degree line cannot be affected by our traveler. So our traveler can at most send signals within its forward light cone, and therefore never to the left of that 45-degree line. So this is a horizon, and that's a horizon for our traveler. And what is crucial about this is that, to keep in mind here, is that this horizon here is given by the line t is equal to x, and that horizon is given by the line t is equal to minus x. So what we have is that our traveler can't influence below the line x naught is equal to minus x prime, or in other words, x naught plus x prime is smaller 0. And it can't be influenced by events above the line x naught minus x1. So the combinations x naught plus x1 and x naught minus x1, which are the trajectories of light that's emitted from that event at the origin, these particular combinations of the coordinates play an important role because they easily delineate where the horizons are, namely where this combination is 0 or where that combination is 0. So these combinations of x naught and x1 can themselves be used as coordinates, so-called light cone coordinates. And they are useful for two reasons, at least two reasons. One of them is that they will easily denote where the horizons are. And secondly, wave equations can take particularly simple forms in light cone coordinates, especially in 1+1 dimensions. So let us move to the use of inertial light cone coordinates. So we take our inertial Cartesian coordinate system, and then we define light cone coordinates out of that. So instead of using our coordinates x0 and x1, we will now choose coordinates x tilde 0 and x tilde 1. And the components of that x tilde vector we'll call u and v. I would really prefer, in principle, to call them x tilde 0 and x tilde 1 instead. But I thought I'd follow here the notation in Mukhanov and Vinitsky so that you can look up that and you don't have to permanently translate between terminology and notation. So the light cone coordinates that come out of our Cartesian coordinate system will be called u and v. And the new coordinate u, in terms of the old coordinate, is the difference between x0 and x1. And the new coordinate v, in terms of the old coordinate system, is the sum of x0 and x1. So u equals 0 is one horizon, and v equals 0 is another. Now that we've changed coordinate system, things change a little bit. In the new coordinate system, in principle, the equations of motion, the action, all of these things will look a little different. And we should start with the metric. How does the metric look like now in the new coordinate system? Well, in the old coordinate system, we had that the metric took the familiar form of 1, 0, 0, minus 1. It was a Cartesian coordinate system. But now in the light cone coordinates, it turns out, and I leave it to you as a little exercise, that when you transform the metric now to the new coordinate system, it takes this a little odd-looking form, 0, 1 half, 1 half, 0. It's got to be symmetric, of course, and this is symmetric. But you see, the diagonal is 0 now. And so the line element also turns out to be just du by tu times dv. How do you calculate that? Well, remember that the metric in a new coordinate system is given by the metric in an old coordinate system, multiplied with those change of coordinate maps. It's just 2 by 2 matrix here, 2 by 2 matrix there. Easy. Okay, so this is the new form of the metric. And that has an impact in all over the place. For example, when you calculate the square root of the absolute value of the determinant of the metric, right? It will impact this. Or if you need perhaps the inverse metric, so g with the upper indices, well then it will look just like this, but instead of 1/2, you will have 2s over there and there. So there are things to keep in mind. Now, we had introduced a trajectory that is of uniform acceleration. We wrote it down in the Cartesian coordinate system. Let us now write down that same trajectory in the light cone coordinate system. So it turns out that the trajectory of our traveler is given by two functions in the new coordinate system, u of tau and v of tau, by the two coordinate functions, which are easily calculated because the u is just the difference between t and x, and the v is the sum of the t and the x. And we know already what t of tau is and what x of tau is, because from our old representation of the trajectory. And the t of tau was a hyperbolic cosine, the x of tau was a hyperbolic sine. And they're just given by exponentials, by sums and differences of exponentials. So if you just plug it in here, you get some cancellations, and this is what you get. The u of tau is an exponential, which is like half of a hyperbolic sine or half of a hyperbolic cosine. And the v of tau also is an exponential. And remember what we said earlier, from the equations that we had before, the traveler can't influence events for which v is smaller 0, and it can't be influenced by events which have u larger or equal to 0, because v equals 0 and u equals 0 were the horizons. Now, if you want to see how the trajectory looks like in the uv coordinate system, in the light cone coordinate system, this is how it goes. U this way, v this way, the trajectory goes like that. If you just plug in these two expressions and run through the parameter tau. See, the u is always negative, comes from here. and it will stay always negative because this thing is always positive, and the v itself is positive, so this is the curve that you get. In principle, the UV coordinate system is just a rotation and a inversion, just a rotation and a flip of a Cartesian coordinate system by 45 degrees. And so now what used to be the forward light cone in the Cartesian coordinate system, like this, in the light cone coordinates, the light cone is actually like that. So every traveler has to have a tangent which is pointing anywhere in between that quadrant here. And as we can see, our trajectory has that kind of tangent. Lines of equal time are this way. Lines of equal position are that way. But never mind, we will not need to use the visuals of the UV coordinate system. So it was really just for illustration. We're not going to build on that. So far we have two coordinate systems. We have an inertial Cartesian coordinate system, and then we took that inertial Cartesian coordinate system and turned it by rotating it a bit, 45 degrees, into an inertial light cone coordinate system. Now let's construct a new coordinate system that is adapted to our traveler, to our uniformly accelerated traveler. Namely, we want a co-moving coordinate system. So we want a coordinate system, and let's call the new coordinates psi. We want the new coordinates to be such that the trajectory of the traveler is tau, 0, which is to say that the traveler is at rest in this coordinate system. The traveler is still aging, but not moving. The position is always the origin. Now, that's a nice requirement to have. Obviously, we want that. That means it's co-moving. But that doesn't fix the coordinate system at all. It just fixes what the coordinates are on the world line of our traveler. It doesn't fix the coordinate system anywhere else. So how shall we continue the definition of the coordinate system away from the trajectory of the accelerated traveler? Now, there are many ways to do that, and if we were the travelers, what would we want? We would probably want a coordinate system in which the laws of nature take the most familiar form. And it turns out that in 1+1 dimensions, you can pose a very stringent condition on your coordinate system to make sure that the laws of nature in your new coordinate system look very much like they look ordinarily. Namely, in 1+1 dimension, and in fact in any two-dimensional submanifold of a higher dimensional manifold, in 1+1 dimensions, we can require that the light cones are still at 45 degrees. We can require that in the new coordinate system, light will still travel at 45 degrees. And mathematically, that means that we can require that the metric takes this form. It's some multiple of the Minkowski Cartesian metric. Why is that the same as saying that light is still traveling at 45 degrees? Well, it's the same because if that's the metric, then the line element squared is given by that prefactor times dx0 squared minus dx1 squared. Right? That's just what the metric does. It tells you how to calculate distances. And to require that a vector is null is to say that the line element along its trajectory is 0. So ds squared is 0. But that means that dx0 is plus minus dx1 if the metric takes that form, with or without a prefactor. So if and only if the metric takes that form, then in that coordinate system, light will travel in such a way that dx1 is plus or minus dx0. Because exactly that is the condition that makes this 0, which is to say that it makes the vector, it makes the trajectory light-like. All right, so that motivates that our traveler constructs a co-moving coordinate system such that not only will the traveler be at rest in that coordinate system, but all light in that coordinate system, all light will travel at 45 degrees still. Which is to say that our traveler will want to set up a coordinate system such that the metric takes this form with whatever prefactor. And here's the claim how you can do this. Under the change of coordinates given in this way, the claim is that we have such a coordinate system. So this is a relationship between old and new coordinates. Okay, so the psi0 and psi1 are to be the coordinates of the adapted co-moving coordinate system. And the x0 and x1 are the traditional inertial coordinate systems of Minkowski space. These two transformation equations relate the old and the new coordinates in this way. We have to show two things. One is that if we define the psi0 and psi1 variables in this way, then we obtain a coordinate system in which our traveler is at rest. And secondly, we want to show that if we take the metric and transform it into this new coordinate system, it still looks like a Minkowski metric, perhaps with a prefactor. So let's first check that in this coordinate system, in the so-defined coordinate system of the x0 and the x1, we have that our traveler is really traveling on a trajectory where the traveler is at rest. Let's see. Our traveler is supposed to be sitting at the origin of the x0, x1 coordinate system. So let's choose x1 to be 0. Let's look at the origin of this new coordinate system. In that case, when x0 is equal to x1 is equal to 0, so we look at the origin, we look at x1 equals 0, I mean the spatial part, the origin of that coordinate system, then we have, if we run through all times x0, we have a trajectory. And what is that trajectory? Well, it's exactly the trajectory of our accelerated observer. Because here we have a times psi0, which parameterizes the time for our traveler. And then this is just 1, this is just 1. And if you remember, these are exactly the equations then for the trajectory x0 and x1 of our observer as a function of psi. So we have indeed that x0, x1, this path, is given by that expression if psi1 is equal to 0 and psi0 is the proper time. So this coordinate system, the so-defined coordinate system, so this map between the psi and the x, is indeed co-moving. Our traveler is at the origin at all time. Now let's see how the metric transforms. So we have the Minkowski metric in the Cartesian coordinates, and now we have to calculate the change of coordinate matrix applied to this and find out what the metric looks like in the new coordinate system. That's a little tedious. I didn't want to waste time on that. I'm sure you can easily do this. Calculate what the metric looks like in the new coordinate system of the psi0 and the psi1, and here it is. The metric in the new coordinate system, the metric as a function of psi, is given by some prefactor that depends on, that is e to the power 2a psi1, there's the acceleration parameter in here, times what looks like the Minkowski metric. So this coordinate system achieves that goal. We will have the equations of motion pretty close to the usual, because at least we will see how close it is to the usual, very close indeed. So far, we've just ensured that light rays still travel numerically on 45 degrees, 45-degree lines. Now, maybe you noticed that there was something weird about the way we just defined the new coordinate system. Namely, you might have expected that the transformation, that I gave you the inverse of that transformation. You see, here I'm expressing the old coordinates in terms of the new coordinates psi1 and psi0. Normally, when you change coordinates, you give the new coordinates as functions of the old coordinates. Here I gave it to you the other way around. It's not really a problem if you want to calculate like the metric change and so on. Instead of calculating the dx by dxi, you can calculate the dxi by dx, vice versa. It doesn't really matter. You just get inverse matrices. But there's a special reason why I did it this way around. And the reason is that it's impossible to do it the other way around. There is no inverse. There is no inverse because even if you run with psi1 through all of R, and psi0 through all of R, even if you allow psi0 and psi1 to run through all of R too, so you consider the entire coordinate system of our traveler, you don't get all events in Minkowski space. The new coordinate system covers less ground. It just doesn't cover all of the universe. It covers only a quarter of it. How do we see this? And you see, one hint is perhaps this one. Yes, well, that's right, but that just gives you half. Yeah. You want to see the quarter, right? Okay, I'll show you in a moment. Let me show you in a little plot. Okay, so why did we map the new coordinates to the old coordinates rather than the other way around? Well, the reason is there's no inverse. And why is that? Well, it's because, as I said, if you run through the xi0 and xi1 through all of R2, then you only get the so-called Rindler wedge of Minkowski space. Here again are the 45-degree lines, as far as I could draw them with freehand. And the Rindler wedge is everything that's inside here. Everything inside, everything between those two 45-degree lines. That is what is called the Rindler wedge part of Minkowski space. Now, the trajectory of our traveler is given by this hyperbola, as we discussed earlier. And the lines of constant psi0, of constant time for the accelerated observer in the accelerated observer's coordinate system are these lines. These are constant time. And constant space are these hyperbolas, just like the one on which our traveler is moving. What we can do is this. We can look at this transformation and consider psi1 to be 0 again. If psi1 is 0, the origin, then running through all values of psi0 gives us the trajectory of our traveler. It gives us this trajectory here, right? So this is what we get. These are the events of Minkowski space that we get when psi1 is 0 and we run through all psi0. Now, if psi1 is not 0, if psi1 is some finite value, well then this is some other constant, some other value, some other number, which may be smaller or larger than 1. But in any case, it's the same number here as it is over there. And the entire trajectory that we get, if we hold psi1 fixed now, not at 0, but some other value, and we run through the psi0, is again a hyperbola. It's just rescaled. It's just rescaled in the sense that the psi0 and the psi1 are just like for our observer, but except for a constant prefactor that's different. What that means is that if we run through all possible values of psi1, from -infinity to +infinity, we get all possible positive prefactors here. And that means that we get all possible rescalings of that hyperbola. If you just take that hyperbola and multiply both this coordinate and that coordinate with a constant prefactor, e to the power of xi1, then you get hyperbolas that go very close here and hyperbolas that are very far. You get them all. Overall, they will cover all of the Rindler wedge exactly once, without covering the 45-degree lines or anything that's beyond. So what that means is that our new coordinate system is nice in the sense that it is a co-moving coordinate system. It's nice in the sense that the laws of nature will take a very familiar look in that coordinate system. But it only covers a quarter of Minkowski space. It covers only the right Rindler wedge. This wedge is often called the left Rindler wedge, is not covered, and the forward light cone and the backward light cone of that event are not covered either. So that means that the new coordinate system reaches only as far as the horizons of the traveler. Now we have a new coordinate system, the xi, and let's be modest. We only want to cover that Rindler wedge at the moment. Now that coordinate system will have, by design, light traveling at 45 degrees. But that means that it might be useful again to use light cone coordinates for it. What if we just rotate our Rindler coordinates xi also by 45 degrees and do a reflection so that we also get light cone coordinates now for it? So with very analogously to what we did earlier, we now take our accelerated coordinates x0 and xi0 and xi1 and take the sum and the difference of them to obtain the accelerated light cone coordinates. So the accelerated light cone coordinate system we denote by xi tilde, and its coordinate functions will be called u bar and v bar, in analogy to what we did earlier when we had inertial Cartesian coordinates, then changed to the light cone inertial coordinates, and we called them u and v. Now we have the accelerated Cartesian coordinates xi, and we change to the accelerated light cone coordinates xi tilde, and we call their components u bar and v bar. In the same way that we did it before, the u bar is the difference between the new time variable and the new space variable, and the v bar is the sum of the two. Now, we can calculate what the metric looks like in that coordinate system. It's easy. Change of coordinates, get the change of coordinate matrix, and you can calculate how the metric tensor changes. And this is how it looks like. Not surprisingly, it takes this form, which is the typical form for light cone coordinates, with this prefactor inherited from the fact that the metric in the accelerated Cartesian coordinate system also has a prefactor. And so the line element takes that form. So you see, now we have 4 coordinate systems. 2 Cartesian coordinate systems, 2 light cone coordinate systems. One's inertial, one's accelerated. For convenience, and because it's going to be really useful later on, let me give you also the map that takes you directly between one set of light cone coordinates and the other set of light cone coordinates. So we can directly map also the accelerated light cone coordinates u bar and v bar into the inertial light cone coordinates u and v. And again, it only works this way around, not the other way around, because the accelerated light cone coordinates cover, of course, only the Rindler wedge. So you can take them and map them into Minkowski space, but the reverse you couldn't do because much of Minkowski space simply doesn't have an image in the new coordinate system because these events may be outside the Rindler wedge. Okay, and the transformation between the accelerated light cone coordinates and the inertial light cone coordinates, that transformation is a pretty simple one. The inertial light cone coordinates u and v are related to the accelerated light cone coordinates u bar and v bar in these ways, these two equations. And notice that there's some nice simplicity in here in the sense that u is only dependent on u bar but not on v bar. And v is dependent only on v bar but not on u bar. So they're just rescalings of another. And that equation has two boxes around it because we'll use it twice again in a very important way. So keep that in mind. The transformation between the light cone, the accelerated and the inertial light cone coordinates is given by this. So there is an exponential, or the other way around, a logarithmic relationship between the u and the u bar, and similarly between the v and the v bar. So this is really encoding that acceleration business. If, for example, the acceleration was 0, if we crank down the acceleration all the way to 0, what do we get? Just a sec. I don't see it now. Yeah, it's not going to be it's not going to be continuous. Yeah, and it shouldn't be because one coordinate system covers the entire Minkowski space and the other just Rindler space. Yeah. Okay. So let's do a summary then of the 4 coordinate systems that we have. If we work in, I mean, we are always dealing with Minkowski space, right? We never introduce any curvature in here, only acceleration. So in Minkowski space, if we choose an inertial Cartesian coordinate system, inertial Cartesian, that's the metric, obviously. If, on the other hand, we choose, for all of Minkowski space, an inertial light cone coordinate system, then this is the form the metric takes with the 1/2, 1/2. Then we moved on to an accelerated coordinate system that covers only the right Rindler wedge of Minkowski space. And we initially defined a Cartesian coordinate system, a Cartesian accelerated coordinate system. And in that Cartesian accelerated coordinate system, the metric takes this form. And that's the reason why we call it Cartesian, because it still looks like the Cartesian metric, except that it has a scaling factor in front of it. And then we took the Cartesian accelerated coordinates and defined in the usual way also accelerated light cone coordinates, for which the metric takes this form with the 1/2 and the 1/2 and this prefactor here. And you can tell the xi1 is actually just 2 xi1 is v bar minus u bar. That's all you need to use here. Notice that these 4 metrics are what is called conformally related. This form of the metric is the same as that form of the metric up to a conformal factor, up to a factor that doesn't have any indices here, that it just multiplies the entire matrix. And similarly, this form of the metric is conformally related to that form of the metric. That is a very useful thing to observe. So the fact that these 4 metrics are pairwise conformally related can be expressed in this way. We can go from one metric to the other metric by multiplication with some factor that we may call omega squared of x. I put a square here just to build into it that it's got to be positive. It turns out that in 2 dimensions, the Klein-Gordon action is invariant under any such transformation. If you take the metric, multiply with a even space and position dependent prefactor, then the Klein-Gordon action is invariant. It's going to be very important because that will explain why the equations of motion in the co-moving coordinate system look so dramatically similar to the inertial equation, to the equations of motion in the inertial coordinate system. So in 2 dimensions, the Klein-Gordon action is invariant under these conformal transformations. How do we see that? Now, first of all, what does it mean? It means that if you take the action for using the metric G, then you can plug in a field and you get out a number. The way you calculate that number is the usual way. You get the kinetic term of the action here. I'm dropping here a mass term. The mass term actually would screw it up. You can't do it with a mass. So for a massless Klein-Gordon field, this is the action. And the claim is that if you calculate the action not with this metric, but with a metric obtained by a conformal transformation, then you get the exact same number out of it. How could that possibly be? After all, this is not just a constant that somehow drops out. It's a position-dependent. It's a position-dependent prefactor there. But the reason is that this transforms non-trivially, and that transforms non-trivially, but together they undo each other. So here's the proof. The metric with the upper indices is the inverse of the metric with the lower indices. And therefore, if the metric with the lower indices transforms with a prefactor of omega squared, then the inverse has to go with 1 over omega squared. So that's the transformation law for that factor G with upper indices that comes up in here. And then we have also the square root of the absolute value of the determinant of the metric. Now the determinant of the metric is quadratic in G, in 2 dimensions. In higher dimensions, it would be to the 3rd power in G. In 3 dimensions, in 4 dimensions, it would be to the 4th power of G. But in 2 dimensions, the determinant of the metric, because it's determinant of a 2 by 2 matrix, is just quadratically scaling with the metric, with the scaling of the metric. So what we have is that the determinant goes like G squared, which is to say goes like omega to the 4th. But we take the square root of it, and that means it goes like omega squared. So the transformation rule for the measure factor in the integral is simply omega squared times the measure. And clearly that's the opposite of what this does. So if you put the omega to the power minus 2 in here, along with the transformation, and you get an omega squared there, that's why it's invariant. So now let's look at the Klein-Gordon action. The Klein-Gordon action is, in general, always this. No matter which coordinate system you choose, inertial or accelerated or whatever coordinate system, that's always the action. Now, if we choose the inertial Cartesian coordinates, then we know that this is the D'Alembertian, dt squared minus dx squared, or dx naught squared, dx naught phi squared minus dx1 phi squared. And it's Minkowski space, so there's no non-trivial factor here from the metric or from the measure. Inertial Cartesian coordinates. If we use the inertial light cone coordinates, then, as is easy to verify, the same action takes this form. And why do we have here d by du of phi times d by dv of phi? Well, it's because in light cone coordinates, the metric doesn't have diagonal terms. It only has those 2 off-diagonal terms, and they are the same, right? You get one term du phi times dv phi, and another term where it's the other way around, dv phi times du phi. And then you get also a non-trivial measure factor, and all of that combines to the impact that the 1/2 becomes a 2. So that phi is easy. Now let's have a look at how the action, and therefore the equations of motion, will look like in the co-moving coordinate system that we constructed for our traveler. So now I'm writing here the action as the action in the Rindler wedge. It's not the same as this action, because that's an action where you integrate over an entire Minkowski space. This is just a part of that action. It's where you cover only the Rindler wedge. So it would not be right to drop that index. It's important to have it there. Okay, so the action in the Rindler wedge is given by this expression here, where we just have d by dt, I mean the time derivative of phi squared minus the space derivative of phi squared. And there is no other decoration in there, nothing non-trivial in here. How come? If we transform that action here into these coordinates, why don't we get any particular extra decorations? Well, we just proved it, right? We just proved that if the metric is changing only by a conformal transformation, then the action doesn't change at all, right? It's the same whether you put a g or g bar in there, or g of x or g of x tilde, it doesn't matter. So because the metric, where are we? Here. Because the metric in inertial Cartesian coordinates is a multiple, it's a conformal multiple of the metric in accelerated Cartesian coordinates, we can immediately write down what the action is. We don't have to go through the calculation anymore. And we can apply the same argument to the light cone coordinates. This is the action in inertial light cone coordinates. We know that the metric in accelerated light cone coordinates is the same metric up to a conformal prefactor. Therefore, the action takes exactly the same form. And we have now the u bar phi, the v bar phi. So this is the derivative with respect to the light cone coordinates u bar and v bar, the accelerated light cone coordinates u bar and v bar. So now we have the action expressed in all four coordinates: inertial Cartesian, inertial light cone, accelerated Cartesian, accelerated light cone. And look at them, they're the same, right? They are technically, structurally, they are the same, which has far-reaching consequences. Yep?
Leading factor of 1/2 or leading factor of 2?
Oh yeah, that should be a 2 as well, thanks. That's right. Just fix that. Thanks. Oh. Okay. So now that we have the actions, let us write down the Klein-Gordon equations. Now, in inertial light cone coordinates, here are the Euler-Lagrange equations. We'll not do it in the Cartesian coordinates. Remember, I promised that the light cone coordinates would be good for something. There's an overhead in trouble with introducing them. That would be good for something, and this is now where we reap the benefit of having gone through the trouble of introducing them. Let us look at the equations of motion that arise from these actions in light cone coordinates. Let's first do it for the inertial light cone coordinates. Then, as usual, the Euler-Lagrange equations take this form: ds by d phi is equal to d by du, d by dv of ds by d du phi, ds by d dv phi. And the equation of motion simply reduces then to this. This is the equation of motion in light cone coordinates. You see, if you calculate it from that action here, then, I mean, for example, do an integration by parts, then the derivative is over here. You have a du, dv, and here just the plane phi. And then in the Euler-Lagrange equations, you have only a contribution from this, not from that. And the contribution that you have from this is just the du, dv phi. So that's the equation of motion in the light cone coordinates. It's beautiful because it's very easy to solve. Very easy to solve because this is solved by any phi, and only, I mean, even if the phi has the form that it is a function of only the first variable plus a function of only the second variable. Where a and b can be arbitrary functions. So you see, differentiate that with respect to v, for example, then you get some expression, but then you still have to differentiate with respect to u, which will give you 0, and that's what it will give you. Now, it's only in 1 + 1 dimensions that you can solve an equation of motion that easily. Now, for example, what would solve the equations of motion here? We are interested in particular solutions to the equations of motion, namely the ones that we need for the mode functions. So we observe, for example, that the function phi of u and v, given by e to the power of minus I wu, is solving our equation of motion. Why is that? Well, because it's only depending on u, not on v. So clearly, that holds true. You differentiate with respect to u, and then with respect to v, it's gone. But let us look at what this function really is, what this solution is. Well, the u is given by t minus x. That was the relationship between the light cone variable u and the Cartesian coordinates t and x. And what we see here is that this is a plane wave. And it is moving positively, it is moving to the right, and it is of positive frequency. Well, I hope you're not too confused about why this is called positive frequency. You see, you have minus I omega t. Why is it called a positive frequency? Well, if you think about the Schrödinger equation, for example, where the energy is I d by dt, okay? The energy, the left-hand side of the Schrödinger equation is the energy. It's I d by dt. If you apply I d by dt on this, then the I multiplies with the minus I to give you a plus 1. So that's why when you have minus I omega t, that's what is called a positive frequency, because it goes with the positive energy. And yeah, and it's moving to the right. You can tell because the phase of that wave stays constant if you both increase x and increase t by the same amount, right? And so that's why it is moving to the right. Okay, so this is a right-moving positive frequency solution of the kind that we would like to use for mode functions. So indeed, and not just would like, that's what we are going to do. So we are still working here. Remember, this is just the ordinary Cartesian coordinate system rotated by 45 degrees so that we get the light cone coordinates. Let us write down the solution to the Klein-Gordon equation, the Klein-Gordon quantum field theory that we developed throughout this course, or very early on already. Let us write that down, but now using the light cone coordinates. So I'm just writing down the usual solution, but I'm writing it in the light cone coordinates. So the phi of x and t, but expressed in terms of u and v, is given in this way, where you have positive momenta, right-moving momenta, and you have left-moving negative momenta, and you have these plane wave factors from the mode functions. You have the usual 1 over square root of 2 omega prefactor there. You only have a factor of 1 over square root of 2 pi, whereas in the older formulas you might see power of 3 here. That's just because we have 3 space dimensions. Now we have only 1 space dimension. And you just have to spell out what the u is, namely it's the t minus x, and t minus x here, and here you have t plus x and t plus x over there. This is a massless field, so the omega is simply the k. I'm integrating here, the k is only from 0 to infinity, when they really run from minus infinity to plus infinity. But I write it as an integral from 0 to infinity simply by writing the terms with the k here, and then what would have been a negative k, I write them over here with a minus k. So I could also just drop those terms and integrate instead from -infinity to +infinity. So we have the right movers and the left movers. Now let us look at the Klein-Gordon equation in the accelerated frame. So our traveler also has a coordinate system and expresses the action in the accelerated Cartesian frame and in the accelerated light cone frame. So how does it look like for the traveler in the accelerated light cone frame? Which, of course, remember, covers only the Rindler wedge. So we calculate again equations of motion. And it goes through exactly the same way as it did before, because the action's structurally exactly the same. The solutions are given again by arbitrary functions a of u bar and b of v bar, where, remember, u bar and v bar are the accelerated light cone coordinates. A and b are arbitrary functions. And in particular, these are right-moving positive frequency waves as far as our traveler is concerned. And so, in the accelerated frame, our observer may say, okay, I write my quantum field in this way, where I'm using these positive frequency modes to express the quantum field. And since these are different mode functions from the one that we used previously, we should also use different creation and annihilation operators. Remember, the same field can be represented in many different ways. And our accelerated observer, using an adapted coordinate system, is writing the same quantum field that we are looking at from whatever perspective, is writing the same quantum field now in terms of new mode functions, new creation, and annihilation operators. You can check that indeed the hermiticity conditions are obeyed, that the Klein-Gordon equation is obeyed, and the canonical commutation relations are obeyed. That's all you really need. Remember that as long as you do that, as long as you fulfill the canonical commutation relations, the hermiticity condition, and the equations of motion, you're fine. You have a representation of your field. And we also know that all those representations are related by Bogoliubov transformations.
Excuse me. Mm-hmm. When you talk about integration from 0 to infinity,
yeah.
You said for the third term, it can also be absorbed into the first term and then integrate from -infinity to infinity. But these two terms have different coefficients.
What do you mean? Well, yeah, but you remember, you have to look at it very, very carefully, because the omega is either k or minus k. And so you have to just spell it out. Just think about it this way. Drop those terms, write the integral from -infinity to +infinity. Right? You can certainly do that. That's how we always did it. And then you say, no, I don't want to do that. Instead, I add two terms. I split it into two integrals from -infinity to 0, from 0 to +infinity, and then I change around the signs, and then in this way you get a third and a fourth term. It's a bit tedious, but yeah. Okay. So now, the inertial observer now may say, okay, I know what state the system is in. It's in the vacuum state. And the vacuum state is the state which is annihilated by the A operators. And we call that state the vacuum state with an M for Minkowski space. Now, the accelerated observer might say, well, or the accelerated observer may find himself or herself in a state where there are no particles. And then the accelerated observer would say, okay, I don't see any particles. That must mean that the quantum field is in a state which is annihilated by my B operators. We will later see that, in fact, that cannot happen. The accelerated observer will not be able to arrange, or nobody will be able to arrange that the quantum field is in a state in which the accelerated observer doesn't see particles. But if it were possible, you would need an infinite energy budget, as it turns out, but if it were possible to do it, then that would be the state annihilated by the BK. So we have two competing notions of vacuum. What is a vacuum for an inertial observer is not necessarily the vacuum for an accelerated observer. For our calculations, let's assume that the quantum field is in that state which the inertial observer calls the vacuum. After all, that's realistic. That's what we can create with some approximation, an actual vacuum for an inertial observer. So what we'll be interested in is this. Assume that the state of the quantum field, psi initial, is the Minkowski space vacuum. And then we consider an accelerated observer. Will that accelerated observer see heat? Will that accelerated observer see particles? If the accelerated thing is a cube of ice, will it melt merely because it's accelerated? That's the conclusion we arrived at when we calculated the Andrew effect in lecture 8. Let's see how we can recover that here. So will acceleration melt ice? So again, the state that the quantum field is in will be assumed to be the Minkowski vacuum. We will later, at the end, discuss what it would take to put this quantum field into the state 0 Rindler. Okay, so we arrived so far at a quite typical situation, typical for this course. We have a situation where the quantum field is expressed in two different ways. The inertial observer set up a coordinate system and mode decomposition and all that, and ended up solving the Klein-Gordon equation, solving the Hermitistic condition, and solving the commutation relations in this way. So the inertial observer is writing the quantum field in this way. The accelerated observer is writing the quantum field in that way. We know that there must exist Bogoliubov transformations linking these two representations to each other. Now it turns out that we can do this separately for the left-moving and for the right-moving modes. And for convenience, we will just not consider the left-moving modes. For the right-moving modes, it will be the same story. What, however, is very important is that, so we will only consider the right-moving modes now. What is important is that the frequencies will mix. The frequencies in time will mix. That is quite different from what we saw in the case of cosmology, where for each co-moving mode, we had a Bogoliubov transformation from its early behavior to its late behavior. But we never had that the co-moving modes were interacting with another, or that they would turn into another, that a late co-moving mode is a linear combination of different early co-moving modes. That never happened, because those harmonic oscillators were not coupled. But here it will be different. We will find that all the frequencies in time mix among each other. Intuitively, it's because what sounds monochromatic to an inertial observer, a monochromatic one frequency in time wavelengths for the inertial observer will sound like a chirp to the accelerated observer. And mathematically, it means that we have to allow that the B operators are some to be determined linear combination of the A and A dagger operators running through over all possible frequencies. There could be a mix. What is a fixed frequency for the accelerated observer is a mix of frequencies for the inertial observer and vice versa. Now I'm writing here the annihilation operators for the accelerated observer in terms of the annihilation and creation operators of the inertial observer. Remember that I could not do the reverse. Could not do the reverse because the new coordinate system, the accelerated coordinate system, only covers the Rindler wedge. So it has strictly less degrees of freedom. So I can certainly express those fewer degrees of freedom given here on the side of the accelerated observer. I can express them in terms of the Minkowski degrees of freedom because they express everything, but not the other way around. Now, here's something that you may want to check as a little exercise. Remember that these obey the usual commutation relations between A and A dagger operators, and these are to obey the usual commutation relations between B and B dagger operators. And that means that you can derive from that simple fact a certain relationship that the alphas and the betas have to obey. If the alphas and the betas were just arbitrary, there would be no guarantee that the B and the B dagger obey the proper commutation relations. No, there's a constraint on the alpha and the beta that must hold no matter what. Independent of whether this is constant acceleration or whatever it might be, the fact that these obey the canonical commutation relations and those means that the alphas and the betas automatically have certain relationships. And here is what it is. So if you just enforce the commutation relations for the B, use the ones between the A and A dagger, you can derive that the coefficients alpha and beta have to obey this consistency condition. We had a similar consistency condition in the case of cosmology, but it was much simpler because we didn't have an integral here. It was basically an alpha modulus squared minus a beta modulus squared is equal to a 1, or Kronecker delta. Because they were not mixing at the time. The comoving modes were so superbly adapted to degrees of freedom that they didn't mix, but here they do. We will keep that in mind, this equation C. We will later need it. Unfortunately, we will need it in the case where omega is equal to omega prime, which is a bad case to consider because this thing explodes. But it turns out that this equation actually only has a divergence here because we are looking at a situation without an infrared cutoff. If you put an infrared cutoff, then you have only a discrete set of k values, therefore a discrete set of omega values, and therefore that Dirac delta becomes a Kronecker delta multiplied with the volume. If the volume goes to infinity, then the volume factor goes to infinity and the spacing goes to 0, and you get the Dirac delta back. Anyway, we'll cross that bridge when we get there. So our aim is to calculate what the alpha and the beta coefficients are. And if you remember from our earlier studies in this course, when you have a Bogoliubov transformation of this kind, what really matters is the beta coefficients, because they tell you how large the quantum fluctuations are going to be. That's going to tell you how much the particle creation is going to be. But we'll have to work out both of them, the alpha and the beta. So already we have a relationship between the alpha and the beta in this. Now let's calculate the alphas and the beta. That's going to be a little tedious. It's a little complicated here. And I'm giving you not all the details. Have a look at Mukhanov and Vinitsky if you want to fill in some gaps. Even though, I mean, basically I'm filling different gaps than they do. So both together, it should be a complete picture. But I'm trying to be as complete enough so that you see exactly how it goes. Okay, so what we do is we substitute, in order to calculate alpha and beta, we substitute equation B in the equation A. Let's see what they are. So equation B was the Bogoliubov transform, and we plug that into the equation that says the field is represented in two different ways. A, the field is represented this way or that way. So if we now take the Bogoliubov transform, we have B is equal to integral over alpha, beta, A, and A dagger. So we plug that in here. Then we get rid of the B. All occurrences of B are replaced by, well, the Bogoliubov transform, right? So it's all A's and A daggers in here. So what we then have, when we put this ansatz for the Bogoliubov transform into this equation, is A and A daggers over here, and A and A daggers over there. Okay, so all we have to do now is to match the A dagger K terms here to the A dagger K terms over there, and the A K terms to the A K terms over here. We just match coefficients then. And when you do this, you obtain this equation. Just by matching the coefficients, you get this equation here. It says that 1 over square root of omega e to the power minus I omega a. A u is given by this integral here. And keep in mind that, I mean, it looks like there's a mismatch because this depends on u, but this stuff depends on u bar. So there's no u in here, it seems, right? But there is. Remember that the u bar is a function of the u, or the u is a function of the u bar. It's the relationship between the inertial light cone variables and the accelerated light cone variables. Remember the equation in the double frame? That's the one we need. The relationship between the u and the u bar. So this is, it perhaps looks like just integrating plane waves, but not so fast. It's not so easy because the relationship between the u and the u bar is logarithmic or exponential, right? So that's going to be non-trivial. What are we going to do? Well, we multiply that entire equation here with either e to the power plus or e to the power minus I omega u bar. And then we integrate over u bar. In this way, we can isolate the alpha, or we can isolate the beta. You see, if we multiply here with this plane wave, and then we integrate over the u bar, then we get Dirac delta functions, right? Because, you know, this is just producing a Dirac delta. We integrate over plane wave. And we get a Dirac delta either in omega prime plus omega, or a Dirac delta in omega prime minus omega. Only one of the two can survive. And we either get the alpha coefficient or we get the beta coefficient out of it. So what we get is the alpha coefficient, let's say, culled out of this expression here by this trick. And on the left-hand side, well, on the left-hand side, we are left with integrating this and multiplying with that. So this is what we get. And the end result, depending on whether we do the plus or the minus, we pick out the alpha or the beta coefficient. We obtain that in the plus case, we get the alpha coefficient. In the minus case, we get the beta coefficient. And they are, as the case may be, the plus or the minus, some prefactor, and then this integral here, which is simply what you get when you take this expression and multiply and integrate over, and then have some remnant coefficient in front of the alpha from here, from the Dirac delta. So that's our end result. We have the alpha and the beta Bogoliubov coefficients, and especially the beta coefficient that will tell us about particle production, expressed in terms of this integral. That integral, though, is not easy. It looks a bit like just the Fourier transform or even integral over plane wave, but it's not, because here you have the u bar, which is highly non-trivially related to the u. No, this encodes the chirp. So we are really calculating here the Fourier transform of a chirp. That's what we do. But how can we do this? So here's that famous equation again, the relationship between the u and the u bar, this chirping business. That's what goes in here. So actually what we are calculating here is the Fourier transform, right? Or this way, the Fourier transform, this is the Fourier factor, and that's the Fourier integral here, of this function, but the u is actually that. It's an exponentiated u bar. So we are Fourier transforming a function which is not a plane wave at all. It's like a plane wave, but its frequency is going like this. It has an exponentially increasing frequency. Well, what did we expect? We have to calculate the Fourier transform of a chirp. That's what we do. That's ultimately what the Unruh effect is based on. The Fourier transform of a chirp, where the frequency zooms up and down. Okay, so we have to plug that into here and then somehow carry out that Fourier integral. And amazingly, that can be done. And here's how you can do it. From this, we can calculate what du by du bar is. That allows us to change integration variable, so that we're no longer integrating over u bar, but we're integrating over u. And we get this extra factor here from changing the integration variable. And because du by du bar is this, but this factor here is simply minus a times u. So that's how you get minus a times u. Now, our integral that we need to calculate is this. The alpha and the beta Bogoliubov coefficients are given by that. Now we're integrating over u, no longer over u bar. And we've now used this equation in a double box to express the u bar in terms of u. And this is what we get. The -1 factor comes from the measure factor, and the other part is just that. See, I'm just using here the fact that e to the power of u bar times something is on the one hand the u, but on the other hand, here we have e to the power of something u bar. Okay, so that's why this term, e to the power I omega u bar, becomes, using this, minus au to the power of that. And the -1, as I said, comes from the measure factor. It looks a little hopeless. How on earth can you Fourier transform this thing? But it turns out we don't have to. We don't have to carry out the integral because that thing is known. It's a well-known function. Up to some decorations, it's the gamma function. It just so happens that this is the gamma function. Remember that Gauss's gamma function is, and Euler's gamma function is given by this integral here. It goes like e to the power minus s, but it also has s to the power r minus 1. And here that's what we have. We have an e to the power of u, and we have a u to the power of something. So we have an e to the power of minus s, and we have an s to the power of something. And so we can match these things and then obtain, therefore, that we the alpha and the beta coefficients of the Andrew effect in terms of these expressions, just some decorative prefactors, because this is, of course, the plain gamma function, and this has some decorative prefactors there. But ultimately, the whole thing is just a multiple of the gamma function, and all this complicated integral is sitting in here in the gamma function. So now we should be close to calculating how much particle production we have. Let's see. First, I mean, ultimately we're interested in this quantity, right? What is the modulus squared of it? It's not easy to read off from this because we take the gamma function at an imaginary argument, and all these things are a little non-trivial. But what we can do is this. We can read off from this equation right away a relationship between the modulus squared of alpha and the modulus squared of beta. The reason is that they are the same except for the sign in here. Okay? So the alpha coefficient is the same as the beta coefficient. All of these things are the same. Only this plus or minus is changing. And from that we can immediately tell that the modulus squared of the beta is this factor times the modulus squared of the alpha. Let us do a consistency check here. Let's say we take the acceleration to 0. Now if the acceleration goes to 0, then this goes to 0, this goes to infinity. E to the power of minus infinity is a very small number, it goes to 0. So the beta coefficient goes to 0. When the acceleration vanishes, the beta coefficient goes to 0, which is what we would expect, because it means no particle production. The accelerated observer, no longer accelerated now, should not see any particles because the state of the system is the Minkowski vacuum. But how many particles does the accelerated observer see when the acceleration is not vanishing? Okay, so in order to calculate that, we just calculate the number operator. So psi in the state of the quantum field is the Minkowski vacuum. This is the number operator for the mode omega of the accelerated observer. And the number operator is, of course, given by B dagger B. Remember, it's the accelerated observer whose excitation level we want to see for the mode omega. And B dagger B, we cannot simply have act on the Minkowski vacuum, because for the Minkowski vacuum, we know that it's annihilated by the A operator. But we don't a priori know how the B operator acts on it, except we just calculated really how it does it, because we can express the B operator now in terms of the A and the A dagger, the Bogoliubov transform. So let's do it. We express the B and the B dagger in terms of the Bogoliubov transforms of them. So the B operator is this expression. The B dagger operator is that expression. Remember, we have to integrate because we have this complete mixture of all frequencies. And then the A operator annihilates that state. The A dagger operator annihilates that state. And we're just left with the only term that can survive under this, in this expectation value, namely where we have an A dagger acting to the right, multiplied with the B, with a beta. And we have an A acting to the left, multiplied with a B star. So we have a B star B. We have the modulus squared of beta. As you may remember, particle production in a Bogoliubov transformation is proportional to the beta squared. All right, so now let's use C and D. Let me remind you. D was the equation that we obtained by observing that the alpha and beta are almost the same, just differ by these factors. So therefore, the moduli of the two differ just by this coefficient here. That is one equation that we're going to use. And the other equation is the one that became singular, if you remember, namely this one. That was the condition, that was the equation that the alphas and the betas have to obey, because both the A and A dagger obey commutation relations and the B and the B dagger obey canonical commutation relations. So this one is always true, and we can use that. And this one is specific for the Unruh case. Now let's use the two of them. You see, we have two equations for alphas and betas, so we should be able to solve for the betas. So we use both C and D, and then we obtain that the expected number of particles in the mode omega, where omega is a mode of the accelerated observer, is given by this integral here. And it turns out to be, if you just plug in those values, you plug in this and the equation above, the one that has the divergence on the right, the Dirac delta on the right, you obtain that it is this. So the expected number of particles is this integral, which is that, but multiplied with a Dirac delta at omega minus omega. Remember, the equation C had omega minus delta of omega minus omega prime, which was the Dirac delta, and that is divergent. But as we discussed earlier, if you put the system into a box of volume V, then you get V times a Kronecker delta here. And the Kronecker delta is 1. So really what this should be with the careful infrared cutoff is just V here. And that means that in a box, we have the number expectation value of the excitation of the mode omega of the accelerated observer being this times V times the Kronecker delta of omega omega, which is 1. So if we divide now that total number by the volume, we get the density of particles. So we obtain the number density as this expression here. You see, we shouldn't be surprised that we had earlier an infinity, because if you have an infinite volume of space, then any finite particle density will add up to an infinity of particles present. And we lose all information, so it makes sense to look at the density of particles. Now let's compare that. This should look familiar, this number density. If you have a harmonic oscillator with energy levels En are omega, the frequency of the harmonic oscillator, just like the frequency of a mode, omega times n plus 1/2. If you have a harmonic oscillator that is exposed to a heat bath of temperature T, then the expectation value of the number of excitation is given by that expression. which means that the traveler's oscillators are excited in that box as if they were exposed to a heat bath of a temperature called the Unruh temperature, which is A over 2 pi. Right? So if you match those two equations, this is the expected amount of excitation if exposed to a heat bath of temperature T, and that is the expected amount of excitation when accelerated at the rate 2 pi over A. And so we see that the two match, and we have an excitation that is as if it were thermal with a temperature of A over 2 pi. Okay, so that is the derivation of the Unruh effect with probability of transformations. Now, on Monday, we'll do the Hawking effect. In preparation for that, let me just point out something about the Unruh effect that we will use then on Monday. Let us consider the question whether the quantum field could be prepared in the Rindler vacuum state. Couldn't the accelerated observer just have a huge vacuum cleaner, and it goes about and collects all particles that it finds to clean up the place and have a vacuum left behind? Could anybody prepare the quantum field in the state 0R, which is the state that's annihilated by the B operators? If so, we would expect that an inertial observer would now see particles. Now, it turns out that in principle, mathematically, you can write that down, but physically, that is not a reasonable state. And that is because it's not physically implementable with a finite amount of energy, even in principle. Why is that? Well, it's because that state, the Rindler vacuum, would be a state in which there are regions of diverging energy density. The energy momentum tensor, the 0,0 component of the energy momentum tensor would diverge, namely towards the horizon. There is a simple intuition for why that is so. Remember that for the accelerated observer, the equation of motion looks exactly the same as for the inertial observer. And so does the action. So the equation of motion is the same. The canonical commutation relations are the same. The hermeticity conditions are the same. If you define the vacuum state the same way, everything is the same. Which means that if an accelerated observer sets up a vacuum state, the Rindler vacuum state, that accelerated observer can do exactly the same thing that what an inertial observer would do, set up a vacuum state. Now, the inertial observer might say, okay, I calculate the energy momentum tensor, calculate the T0 component to get the energy density, and would get some answer. It turns out to be infinite, but never mind, it can be renormalized. So it's finite. And the accelerated observer could do the same thing. Same action, same equations of motion, same definition of the vacuum, calculates the 0,0 component of the energy momentum tensor, it comes out to be infinite, renormalizes, comes out finite. So it would seem that there's no difference. I mean, why not? Why shouldn't the accelerated observer be able to set up a vacuum state that is his vacuum state? Well, the thing is this, that if the Rindler observer therefore has a constant energy density, vacuum energy density, then that's not a constant vacuum energy density for the inertial observer. And the reason is, I mean, first of all, T0 is not a scalar. T0 is a tensorial quantity. If you change coordinate system, it can change value. And now, we know in inertial, for the inertial observer, if you renormalize the vacuum, everything is constant energy density. For the Rindler observer, it would be the same thing, constant energy density. In the Rindler observer's coordinate system, which covers only the Rindler wedge. And now the important thing is that the Rindler observer has his psi 0 and psi 1 coordinates run through R3. Okay, they run through R3. sorry, R2, right? They run through R2, but they cover only the Rindler wedge. Now in R2 of the psi0 and psi1 coordinates, the energy density is constant in the Rindler vacuum. It's constant. But then if you transform that R2 into the right Rindler wedge, you see that an infinity of the Rindler coordinate range is squeezed into a finite range of in Minkowski space in the inertial coordinate system towards the horizon. So what looks to the Rindler observer like a constant energy density in the Rindler vacuum will not look like a constant energy density at all for the inertial observer. Because for the inertial observer, all of that constant energy density is not constant. It's very much piling up towards the horizons u equals 0 and v equals 0. And that shows up in the coordinate transformation then. The T0 component, the energy density, actually piles up and diverges at the horizon. Let's calculate that. Okay, so let's look at the energy momentum tensor for a massive scalar field. It looks like this. So what that means is we have to study terms of the form, derivative of the field squared. That kind of term will come up. And we want to calculate that for the Rindler vacuum. So now let's concretely calculate this. We calculate the Rindler vacuum expectation value of, for example, d by du of phi squared. It's one of the terms that comes up when you want to calculate the energy momentum tensor, let's say the 0,0 component, in the Rindler vacuum. Let's say if the inertial observer wants to calculate that, if the inertial observer wants to calculate what the T0 is, for example, anywhere in the right Rindler wedge, then that's what the inertial observer has to do, calculate terms like this in the Rindler vacuum state. Now, that's the derivative with respect to u. Let's turn that into a derivative with respect to u bar. So we have now d by du bar of phi squared, and we get by the chain rule a factor of du bar by du. Okay, now let's again recall this famous formula in the double box here, which relates the inertial light cone coordinates to the accelerated light cone coordinates. From that, we can calculate again what du bar by du is. It turns out to be au. So therefore, we can continue this calculation, this thing that we need to calculate to find out what the energy density is in the Rindler vacuum from the perspective of the inertial observer.
Should that be minus au?
Du by du bar, you get a minus down there, right? Right, so du by du bar, you get a minus a down there. So it's just, so it is e to the power of minus a u bar. And that is, yeah, you're right. Thank you. Okay. Yep. Luckily, it doesn't propagate that mistake. Okay. Right, so let's continue that calculation then. Remember, we started with the unbarred u because that was just a regular light cone coordinates. This is the calculation, therefore, that an inertial observer would do. Now we turned it into something that we expressed it in terms of a quantity that the accelerated observer would care about. So we can write this desired matrix element here that has to do with the energy momentum tensor in this way. It's 1 over a u squared, and the error doesn't propagate because we have to square it, because of this being squared, because of the derivative of the field occurring twice. And so that's the expression now. Now, let's see. It turns out that this expression here is, well, let's look at what it is. We are calculating here the derivative of a field with respect to the light cone coordinates, the accelerated light cone coordinates, for the accelerated observer's vacuum, it turns out that this has to be the same number as what we get when we calculate with respect to the inertial light cone coordinates, the derivative of the field, and then calculate the Minkowski space vacuum expectation value. And the reason is that the calculation of this is identical to the calculation of that. Remember that for the accelerated observer, same action, same equations of motion, same commutation relations, hermeticity, everything is the same. So if they both mean the same thing when they say, I'm going to construct my vacuum and I'm going to calculate some vacuum expectation value, then they must come to the same conclusions about what that number is and what that number is. So they are the same. So we can continue our calculation of this crucial component of the T0 energy momentum tensor, and we arrive at this conclusion, that it is this. But this is a value that we know is finite, because this is the energy momentum tensor's matrix element for an inertial observer in the inertial observer's vacuum, right? Inertial observer's vacuum, inertial observer's energy momentum tensor, because it's a derivative with respect to u, not u bar. So it's the kind of term that arises when an inertial observer is calculating the energy momentum tensor. So this thing is finite after renormalization. So what we've just related is the energy momentum tensor calculated by an inertial observer in the case that the vacuum is the Rindler vacuum. And we've expressed that, we've expressed the energy momentum tensor, that you would see as an inertial observer if the state of the field is the Rindler vacuum as a multiple of a finite value, namely the energy density in Minkowski space for the inertial observer, for an inertial observer. And this quantity now, and that's the crucial observation, that quantity now can diverge. It diverges when u goes to 0, which is to say when t is equal to x1, or when x0 is equal to x1, which is to say on the light cone. On the light cone, this thing diverges, which is to say that the energy density, as observed by an inertial observer, diverges towards the light cone if the vacuum is the Rindler vacuum. So the Rindler vacuum, so what's happening is this, that if an accelerated observer is setting up a vacuum state, a Rindler vacuum state, then for that accelerated observer, everything is fine, it's just a vacuum state, the energy density is fine too. But because all of R2 of the accelerated observer gets squeezed into just a wedge, then where the wedge ends at the horizon, you have a piling up of that vacuum energy density so that it actually diverges. So for an observer who is inertial, the energy density T00 component actually diverges towards the horizon of an accelerated observer. So that means that it's not possible actually to set up such a state, because you would have to create an infinite energy density there at the horizon. And actually you can show the same thing not just for u, but also v. So it applies to both the future and the past horizon of the accelerated observer. Right. So we will later need that argument to derive Hawking radiation, because there will be similarly different possibilities for what the vacuum state might be, and the observation of energy density being finite or not finite will be crucial for determining which state it is. Okay, that's it for today.